Hello everyone. So today I will be solving this very hard problem, remove boxes. So the problem states that we are given several boxes with different colors represented by different positive numbers. So for example here like 1, 3, 2, these represents the different colors of the boxes. Now in one round what I can do is remove means choose some continuous boxes with the same color, for example 2, 2, 2, and we can remove them, and after we remove them we will get means gain some points which will be k into k. So k will be the length of the continuous means the number of continuous boxes that are removed with the same color. So we will gain k square points. Now we need to return the maximum number of points we can get, such that like after we'll be removing all the boxes from the given array. So for example in this given input, if we first remove this 2, 2, 2, so the new array will become 1, 3, 3, 4, 3, 1, and we would have gained points of 3 lengths. So 3 into 3 into 3 equals to 9, right? Now either we can like remove this part to try to like create a sequence of length 3 again of color 3, or we can like remove 3 as well. So let's try to remove this. So if we remove this, we'll gain one more cost. 1 into 1 equals to 1. And the new array will become 1, 3, 3, 3 and 1. Now if we remove this part, then again we'll get like 3 into 3 equals to 9. And the new array will become 1, comma 1. And again if we length 2, then we will gain 2 into 2 equals to 4. And as we can see, the overall means sum that we get is 23. And this is the the optimal way of getting 23 output here in this case. So what you need to do is remove some continuous sequence of boxes with the same color, and the score that we'll gain will be the square of the length of means the number of elements that we are removing. Let's see another input. So as we can see, like here we have 1, 1, 1. So if we remove all these ones together, so we'll gain points 3 into 3 equals to 9. Okay. Similarly here we have a single one only. So if we remove this, we will gain 1 into 1 equals to 1 point. Okay. So like, and we will also notice that the constraints are up till 100 only. So maybe we need to think of an approach of the order of n cube or more, right? Then only the constraints would have been given this much for a hard problem, right? So like the first intuition you might get is, can this problem be similar to MCM, the matrix chain multiplication problem? If you are if you have already seen the matrix chain multiplication method, then you will realize like maybe this problem is same as matrix chain multiplication, but it is not. Why? Because in normal matrix chain multiplication, when we means merge the left and right part, when we merge them, we do not like, there is a fixed cost. There is a fixed cost for merging. But here what will happen is, as soon as we remove these two and merge these two parts, we'll create a bonus, means left plus right. Means we are creating a bonus kind of thing at each step, means while merging. And MCM will not be able to account this bonus that we will be creating. For example, if we remove this 2, then suppose here, so when you remove this 4, the left part was suppose this and right part was suppose this. So in normal MCM, when we try to merge it, this bonus will not be able to account, like 2 plus 1. Either it will be 2 or it will be 1. It will not be able to like account the means the bonus, means the way the matrix chain multiplication code is written. So this will not be feasible here. So it is sure, means we should be sure like this can be solved using DP only, because we need to maximize number of points and we need to solve a problem for a complete subarray, and the means the array is getting modified at each steps, right? So we must like think in the direction of DP only. Now the main question is how, means the main question is how do we define the states? Okay, how to define the states? So for example, let's define the states as dp of ij, the simplest state that we can think of, which denotes the maximum number of points that we can get points for array I till j. Okay, so we just need to find dp of 0 till n minus 1. Let's define the simplest dp and try to see whether we can solve it using this dp or not. So let's again write the same example. We had 1 3 3 2 2 2, then 4 3 and 1. This was the problem. Now in this normal dt, what we'll need to do, suppose we need to solve this problem. So at each step, right, dp of I will be 1 only, because one length means either we remove this or this or this. So the maximum point we will gain is 1 only. Now for 2 length, what we'll do, suppose we try to solve, means we are calling dp of ij. So how will be like calculating the maximum points for this state? So definitely like we'll be picking some, means we'll be removing some boxes, right? So now how do we remove those boxes? So for example, suppose we like try to remove some boxes. So this is the current state I till j, and we try to remove some segment in the between, and this segment can be anything. Okay, anything of continuous sequences. Continuous means same color. So what we can do is take another loop of k which will go from I till j. Okay, I till j, and what we will do, it will identify the continuous segments and solve that segment. Now what we will do get is, suppose we remove some segment from k1 till k2 index. Okay, and get a cost of k2 minus k1 plus 1 ka whole square. Alright, now the new dp states will be dp of I till k1 minus 1 and dp of k2 plus 1 till j. Okay, these will be the two states. Now the problem here is that when we do this, and suppose it was the case of here it was 3 3 2 2 2, and suppose it was 3. Now these were the I to j, and we removed this portion. Okay, so the new dp is, new dp was dp this, dp1 and dp2. Now the problem here is that for k2 plus 1 to j and I to k1 minus 1, will not be able to recursively know what how many elements we need to remove from the left part of this, from the right part of this, and from the left part of this, right? Because in the brute force manner we will pick some sequence and remove the continuous sequence from between I to j, right? But we will not be able to, while we have the two new states, we will not be able to merge them such that we will account this 2 and this 1, because there can be like multiple states like this. For example, here also it was 2 to 2, and then again a 3 was there. So suppose if we remove this, then we need to add this as well, right? So this merging thing will not be able to do in this normal dp. I hope like you now understand like why I will not be able to, because the entire array is changing. What we think lies in the right of this index will not be 2. We need the 3. So since this entire nums array is being modified, we will not be able to use this simple dp thing to solve this problem. So what is the problem here? The problem here is that once we removed this 2 to 2, we wanted to solve, suppose this was the, so let me write it again. So suppose this was the problem, 3 3 2 2 2 and 3. Okay, indexes are 0 1 2 3 4 5. Suppose you removed this thing. Okay, now you called dp of 0 till 1 and you call dp of 5 till 5, and you increased score by plus 9. Okay, length 3 into 3. Now the problem here is that we do not know for this like the number of 3's that are present on right. Like since we need to calculate dp of I comma j, so to solve, suppose we remove a segment starting from j, right? So we must know like the number of continuous sequences present on the right of it which is the same as j, right? For example, the next sequence present after 3 is this 3, but we are not aware of it, right? So if we are not aware of it, let's make the DP aware of it. So how we'll modify our DP? Since we are not aware about the number of like 3's appearing on the right, which is part of this continuous string. So what we can do is we can create, means keep this same I to j. What we need is a count. So let's maintain a new variable k, which will denote, what will it will denote? It will denote the number of extra boxes of color what? Of color nums of j. Okay, so the color which is present at this jth index, we need to find out the number of extra boxes we have, which we can utilize to increase, means initially it was k square, so we need to make it k plus 1 square or k plus 2 square. So we want to increase this, right? So suppose we had k boxes, so we need to increase that count. So if we maintain this number of extra boxes of colors nums of j that we have after, means after jth index, that means it is a continuous sequence, means it will form a continuous sequence with this element. So for example, here it will bp of 0 1 and we'll have one extra element, right? We'll have one extra element on the right and we can utilize this value. Okay, so now the dp of I, j, k state we have defined, and let's try to solve the problem whether we can solve it using this state. So it denotes maximum number of points we can get in array I till j with, what do we have in array I to j, with k boxes of color nums of j on the right. Okay, this is what we define it. For a we need to solve this for this subarray, and we should have k boxes on the right whose color is same as this, the element present at the rightmost part of our subarray. Okay, now how do we now once we have defined the DP state, we need to see how the states will be changing and whether we are able to cover all the cases or not. So one case here which can be is we remove a sequence, case 1, remove a color, means box of color nums of j. Okay, so we remove the box which has the color nums of j, here this. So we had the sub problem I till j and we had k boxes of color j, here this one same. Okay, so what if we try to remove this portion? Alright, then what we'll get? We'll simply get, we will need to solve the new problem dp of I till j minus 1, and we now what the k number of k's on the right will be? It will be 0 because we have utilized, means this j here. Alright, so this portion will be solved. Okay, so we have utilized all the k colors, so it will be 0 and we need to add the cost. So cost will be this k plus we have one more box of color nums of j, so it will be k plus 1 ka whole square. Okay, so this will be the cost, for in this case the dp of I j k will be dp of I comma j minus 1 comma 0 plus k plus 1 ka whole square. Alright, this is the case. Now here we removed j, but what if we did not remove j, we remove some middle segment. Okay, so now the second case is we remove some middle segment because this will be the more generalized one, right? We remove some middle segment. So what will be the most optimal way of removing this middle segment? We'll remove this middle segment such that if we have the array from I to j and we have k boxes of color nums of j, so we remove this means portion in such a way that if we have this index as, if we find an index m which has boxes means nums of m as the same as nums of j, then we need to remove in such a manner such that we will be able to merge this box color with a same color as previously. Then only like the cost will increase by a square, right? So initially we had this k and this k plus 1. Okay, so k plus 1 square we already have. Now if we remove some segment from this, then we need to like make sure to remove in such a manner such that this k plus 1 further gets improved to like k plus 2 square, then k plus 3 square and so on, right? Means to increase the power of 2, increase the square as much as possible so that the cost is increased by a larger factor. So this is what we will do. We'll like identify those points where the num means whose color value is same as the rightmost part. And since we already have k boxes of color this, so what will now the new problem will be, since we are removing this part, instead of modifying the nums array, what we'll need to solve is we'll simply need to solve dp of I m. Now the color is m, and since we maintained the number of like equal colors means the number of extra boxes we have on the right, so it will be this and the k boxes, so it will be simply k plus 1, right? Because we removed the portion from m plus 1 till j minus 1. Okay, so the new portion we made it in such a way that now it has, we need to solve this subarray only, and it will have k plus 1 boxes of same color as this, which was same as nums of j. Okay, so this is the subproblem which will divide, and will divide it into plus dp of m plus 1 till j minus 1, and it will have 0 colors on the right because no colors are present. Okay, so this will be the second case. So as you can see, like removing this some middle segment will cover all the generalized cases for means removal. And the problem that we encountered previously, how we have tackled it. So initially when we are removing this 2 to 2, we are not able to maintain like after these 3 how many 3's we have on the right, right? Because we can only solve as means we can only utilize the indexes in a particular order. We cannot modify these elements, like we cannot modify this 2 with 3, right? So we need to like solve this dp subproblem only, but we also need to know how many 3's now we have on the right. So hence from that we got an idea of like we can maintain the number of boxes which we have of the same color as this. And if we just need to solve this simple problem, we'll maintain like we have one value. So dp of 0 1, and we have one color extra in this case. So similarly what we try to do here, we need to solve the problem for I to m, and we have this 1 means one color here and k here. So we have total k plus 1 boxes of color nums of m, and we'll simply solve the subproblem of m plus 1 till j minus 1, which has now 0 colors on the right because we have removed the entire segment. Okay, so this is how we'll be dividing the subproblems. In case where we remove this j only, so we'll remove this j so that the entire sequence is taken, so that we maximize the square. And so we remove all the k plus 1 elements, and it will be the new subproblem will be dp of I to j minus 1 with 0. So I hope you are able to see. Let's try to see for a given input result. So suppose it was 1 to 1. Okay, now initially what we need to calculate, final answer will be in 0 1 2. So dp of 0 to 2 with 0 elements on the right with color 1, right? because we do not have any boxes of color 1 on the right. We need to solve this. Now what are the cases? The cases is we remove this, like we utilize case 1 here. Case 1 was k plus 1 square and dp of ij minus 1 0. So we call dp of 0 1 and k was 0, so plus 0 plus 1 square. Okay, this was the case 1. Now we need to solve this problem. Again we can either solve it in, either we will remove this or we need to find some 2 before, but no 2 exists because we need to find some m which is same as nums of j, right? So here we'll simplify it to dp of 0 0. This is dp of 0 1 0. So dp of 0 0 0 plus what? Again 0 plus 1 ka whole square, and this one is already there. This one is already there. Now this will give us result 1. So 1 plus 1 plus 1, which gives us 3 only. And another way we could solve is, instead of like removing this j, we could have find out, we know that 1 exists on the left, means this m index we can find, right? So what if we find this index? So the value will be dp of I to m. So I will be 0, m will also be 0. So 0 till 0, and we'll have k plus 1. So initially k was 0, so it will be k plus 1, which means 1. Okay, and we solved this subproblem separately, which will be m plus 1 till j minus 1. So dp of m plus 1, which will be 1, and j minus 1 will be 1 and 0. Okay, now this will result in answer 1 because a single length sequence. And for this, what we have? We have 1 only. And since we know like nums of j, this will be the first case. This nums of j is same. So if we remove this nums of j, then we'll have k plus 1 elements, right? This means 1 element is already on the right. So it will be k plus 1 ka whole square plus dp of what? Plus dp of I comma j minus 1 0. So it will be 0 comma minus 1 and 0. So since we will be calling it in a recursive function, so as soon as like L becomes greater than R, so we'll simply return 0. Okay, so we do not need to like means separately check for negative indexes. We'll simply return 0 if L is greater than R. Now, and this k was 1 here, so 1 plus 1 whole square is 4. So hence the optimal cost was 4 plus 1 equals to 5 in this case. So I hope like you are now able to see how we are utilizing this k variable, that we extra variable that we created, to keep count of the number of boxes we have on the right which has the same color as nums of j. Okay, and using these transitions we'll finally be able to solve the problem. As you can see, also we can see like the n is till 100. Okay, so dp states will be of means 100, 100 and 100. Like the maximum we can have 100 elements on the right with means same color as nums of 100, and this indexes will go till 100 on. And in each dp calculation, what we will do, we'll try to find the m. So using a loop we'll try to find the m. So this loop will also go till a big of n only. Okay, so this will be, in the worst case, will be 100 ki power 4, which is 10 ki power 8. And since like space complexity of 1e8 is not allowed, but time complexity will work here because of the because in the recursive function many of the the states will be skipping, will not be calculating values for those states. So in like it will work in approximately 2 seconds, I think. Okay, if the space complexity would have been of the order of 1e8, then it would not have worked. It would have given us Emily, but here it would work fine. So let's see the code of the discussed approach. We'll be like using the two transitions that we had here, and yeah, so let's see how the code looks like. So this is the simple code that we have. We create the dp variable of I, j, k, and what we'll do, if at any point this I becomes greater than j, that means we do not have any subarray. right? This is the subarray. This is not any subarray, right? So we'll simply return 0. Now we'll see if this problem has already been solved. If it has been, we will simply return its value. Else we'll follow. So we'll remove the jth element. We'll remove the jth element. So the new state will be till I till j minus 1 with 0 and plus the k elements that we had, k plus 1 ka whole square. Okay. So this is what we get when we remove this j. And else if we remove the middle part, so that means we need to find some m whose value is same as box of j. So we find this m, and what will be the new subproblem? It will be I till m minus 1 with, means I till m with k plus 1 and plus dp of m plus 1 till j minus 1. Okay, with the zeroth count. So this is what we do. We call the memo function for m plus 1 j minus 1 0 and the memo function for I comma m with k plus 1 count, so with the increased count. And finally we'll maximize the result for the current state and we'll update the dp result. And in the main function, what we'll do, we'll call the function for like a memo of, we'll call memo function with 0 till n minus 1 with initially we have 0 case on the right. So this is the approach for this problem. Let's see the code as well. So let's see the code and try to submit it here. And as you can see, like it runs pretty fine and space required is also very less. So this like was the approach of this problem. I like this problem is means really hard. Solving it on your own is pretty difficult because thinking about the DP states is the main part. And to think about this, like we'll maintain the number of boxes of same color that we have on the right is difficult, but we can follow it intuitively on the basis of this logic. Like we will not in normal DP, why our normal DP is failing, why normal DP fails. If we try to think in that direction, then maybe we'll able to think like if you can maintain the number of same colors that we have on the right, then we will be able to solve it. And if we head in that direction, then this problem is solvable. So there may exist like other approaches as well, but this was the like the simplest approach that I could think of. So yeah, if you have any doubts yet, feel free to comment down and I will be happy to help. Thank you for watching.